Welcome, Calculus AB. This is lesson 6.5, volumes of solids with known cross sections. Let's go. So this is a new concept for us. So before we did area, we were integrating. We were finding the area. We did function f of x from a to b dx. And this finds the area under the curve. Area is a two-dimension shape. Now we're going to talk about volume, which is three dimensions. Well, how do you find the volume of a shape? And what do you mean by a volume? So basically, we're using that area, the integrating to find area, and then somehow we're popping that area up and turning it into volumes. And one way this happens, well, before we get to this, let's talk about what we mean. How do you have an area and define volume? So what you actually do is you're integrating, if you integrate a line like a function, that's like something in one dimensions, this gives you an area. So integrate, f of x equals x squared, it gives you an area. This is a line, it's curved. When you integrate it, it gives you area, which is two dimensions. So following that logic, if I integrate an area that's two dimensions and I integrate it, I get a volume, which is three dimensions. Right? Kind of. So here's the general formula. A volume V equals the integral of an area. So it's integral a to b of an area. Cool. Now, the key thing to do this is area, a right here, we need the formula for that. So a is some kind of function that represents the area. Now, when we're doing it in this case, we're going to talk about cross sections, okay? So what are cross sections when you have a 3D figure? Well, cross sections, we create something 3D, and they're made out of shapes. Maybe we call like a bunch of circles. I'll show you some pictures of this later. So we're going to go way back in time, about 3 years ago, and we're going to talk about our geometry formulas, like formula for a square, side squared, rectangle, base times height, semicircle, well, a whole circle's talking area is pi r squared, so it's 1/2 pi r squared, one semi half. Triangles half base times height, equilateral triangle. I don't think this really happens, but it's in the notes. Why not? Write it down as reference. So if you probably don't know this, I wouldn't know it. So before, no, I don't want to do this. I want you to watch this first. Watch this animation. Just sit there, listen to music. I'm turning on my music. Just see what's going on. It's growing some cross sections. Isn't that amazing? So we're growing cross sections. Okay, stop it right here. So, Spotify and ads. Okay, I'm going to handle that. So what's going on here is you see it's growing cross sections. Now we have the shape of a triangle, this area right here. And let's say this is area between two curves. We're going to call this one f of x and this one g of x. So trying to find the area between those two curves like this, right? And that's f of x, this g of x. Now this is what it looks like if you grow a bunch of squares. This could be what it looks like when you're growing a bunch of triangles in this one. And this one, we actually grow a bunch of semicircles. So basically you're cutting up a bunch of these little shapes to kind of give it its figure. This triangle one right here, it's using the squares. It would look different if I used semicircles instead. And it would look different if I used triangles in the triangle. So that's what we mean when we say by cross sections. We have some shape that's growing along the area between the two curves or whatever. All right? So the key to solving these kind of problems, and this is like one of the hardest things to do in calculus, so it's going to take a while to learn. So you got this formula, your area, right? First of all, you got to figure out your limits a and b. So boom and boom. And if I'm looking at this problem, my limits here would be that'd be my a, and over here would be my b. So a to b, a to b, a to b. All right. Then you want to, sometimes it's given to you. So what shape are the cross sections? Somewhere it's going to say like squares or rectangles or something else, and you're going to use that formula. So these kind of problems, they tell you what kind of shape. And then the trick is to figure out that a. So the variables in the area formula might be constant or might be one of the functions. So part of this is changing now. Like we know what it is if it's a square. Like how do we kind of write that formula? And that's sometimes the hard part. This is where you got to practice a little bit. So before I get into that, let's just kind of do some problems. So let's show you this shape. Find the volume of the solid whose base is a triangle bounded by this and this and this, and whose cross sections are squares. Okay, so who cares if the base is triangle? They're trying to trick you out. Cross sections are squares. So that means the area formula is going to be squares, which are perpendicular to x-axis. So I'm going to draw a picture of what that looks like. Perpendicular to x-axis means the squares are kind of popping out like this, kind of like this shape. Oh, I'm a really bad drawer of squares. It's kind of hard to draw 3D for me. But hopefully you get the idea. It's like they're popping out like that, maybe. Okay, so and then this line right here is obviously the negative 2x plus 2, and then we have between x equals 0, which is right this line right here, the y-axis, and y equals 0, this axis. So it's basically this triangle right here. So this would be the area we're using. And we have cross sections growing out of this. All right, so setting up this formula, what's the upper and lower limits? Lower is going to be 1, and or bottom 0 to 1, so 0 to 1. And the area of a square, area equals s squared. So side squared is your square. What's the formula for one side? And this is where it's usually going to involve variables. Notice that a length of one side is changing. This one is a lot longer for the square than this side. Well, what's it based off of? Notice here, it's just based off this height. The length of this is the height of this function. It's basically whatever this is. So our s in this case is going to be this function right here, negative 2x plus 2. It's basically just our y function. And a lot of times your answer to these problems are basically going to be one of these functions. So when I set up this volume, or your integral right here, it's going to be integral of 1 over 1 to 0 of negative 2x plus 2 squared dx. That's it, and then I just integrate from there. So let's integrate. So again, that's negative 2x plus 2 times negative 2x plus 2. I'm going to FOIL that out, so that's going to be positive 4x squared minus 4x plus 4. So that's going to be the integral from 0 to 1 of 4x squared minus 8x plus 4 dx. And you can kind of go from there. So let's say it's going to be 4x cubed over 3 minus 8x squared over 2, which is minus 4x squared, plus 4x from 0 to 1. So plugging in the 1 would be 4 times 1 over 3 over 4 over 3, minus 4 times 1, minus 4, plus 4. And then when you plug in the 0, it's just minus 0 for everything. So these cancel out. Minus 4 plus 4, so my answer is actually 4/3. All right. A lot of work sometimes, but there you go. So I want to set up an integral. So let's take that same exact problem, and instead of cross sections being squares, they're going to be semicircles. So coming off the line right here, again, a flat line, they're going to look like this coming out. That line look like this. Flat line, semicircles coming out like that. Okay, in the area of a semicircle, so it's integral from 0 to 1 still. And the formula for a semicircle is 1/2 pi r squared. Okay, so I can actually put this as 1/2 pi and then your r squared dx. We got to figure out your formula for your r. R stands for radius. Your radius in this case, it's not going to be this whole line. So radius, when we're talking circles, is only half that line. Diameter would be the whole thing. So my r in this case is not going to be negative 2x over 2. It's going to be negative 2x plus 2. It's going to be half of that divided by 2. So my r is negative x plus 1. So my formula, I can write integral from 0 to 1 of 1/2 pi times negative x plus 1 squared dx. And this is a constant. I'm going to actually write it outside. I can write it as pi over 2 integral from 0 to 1 of negative x plus 1 squared. I don't have to. I just did that. Just a reminder, you can. Either way would have worked. And don't integrate. All right. So I think I did some examples. I don't want to keep doing a bunch because that'll kind of bore you. We'll do those in class. And we're stopping.